In this episode, we are going to calculate the moment of inertia of a solid circular area with respect to the x-axis that crosses the center of the section. So, as we have mentioned in other episodes, we need to define this dA, the differential area. There are different ways you could do it, but in this case, I am going to define that differential area as a horizontal slice of thickness dy and a width which varies as a function of y. Right? So in this case, that variation is given by the equation of the circle, right? If we remember, the equation of the circle is r squared equals x squared plus y squared. That defines the edge of the circle. And so if we want to define this width, if we are at a height y, the width x is going to be r squared minus y squared square root, right? So that's the distance x corresponding to a point at a height y. Right, so this would be x, would be y. That would be that distance from here to here. The total width is twice that. So then this dA becomes 2 times square root of r squared minus y squared times dy. That's b, 2 times that x there, times the thickness. We calculate that for all y's from 0 to r, and then we simply multiply that by 2 to account for the lower half of the circle. So this integral will be 2 times from 0 to r of 2 times square root r squared minus y squared times y squared dy, right? This y squared goes here. Now we have to solve that integral. Let's organize a few things here. We're going to say that this moment of inertia would be equal to 4 times the integral from 0 to r of y squared integral r squared minus y squared dy. Turns out that this integral has a closed form solution. You can find them in integral tables. You can try to work it out on your own using the rules of integration from calculus, using chain rule, for example. I'm going to give you here how the answer looks like. That integral is equal to this y times r squared minus y squared to the 3/2 divided by 4 plus r squared times y times the square root of r squared minus y squared divided by 8 plus r to the fourth divided by 8 times the inverse sine of y over r. So it has three terms. And all these terms have to be evaluated from 0 to r. And then multiplied times 4. So that integral equals this. Now let's first start evaluating at r. So first of all, when we put r in here, so if we evaluate at r, the three terms, the first term is 0, because you got r squared minus r squared, this cancels out. This cancels out too. And this, when you substitute y for r, you get the inverse sine of 1, which is equal to pi over 2. And so you get the first term 0, the second term 0, and the third term is r to the fourth divided by 8 times pi over 2. Now we evaluate at 0. When we put y equals to 0, this term cancels out because of this y. This term cancels out because of this y out here. And this term cancels out because the inverse sine of 0 is also 0. So all three terms vanish and we are left with this term. So the integral times 4, so the moment of inertia is 4 times r to the fourth divided by 8 times pi over 2, which results in r to the fourth times pi divided by 4. But let's write that a little more clear right here. Moment of inertia will be pi r to the fourth divided by 4. And that's the answer. So actually we had to go through some pretty interesting mathematical expressions and not a trivial integral, but eventually when you boil it all down, it boils down to pi r to the fourth divided by 4. So that's pretty interesting. The other thing to consider, which I'm going to erase some of this now, is to compare the moment of inertia of a rectangle, or in this case of a square, in which a circle is inscribed. So when you compare the moment of inertia of this square right here, in this case it has dimensions 2r, 2r, so the moment of inertia of the square is 2r times 2r cubed divided by 12, so that brings you 16 r to the fourth divided by 12, which comes out to approximately, so 4/3 r to the fourth, approximately 1.33 r to the fourth. Right? So this is the moment of inertia of this square, which is, and then the moment of inertia of this circle right here, inscribed in that square, like we've just found, is pi r to the fourth divided by 4, which is approximately equal to 0.785 r to the fourth. So if you compare that number, this number, you see that the inertia of the square is almost twice as big as the inertia of the circle that is inscribed. However, if you compare the areas, if you compare the area of the square, which would be 2r square, that would be 4r square, versus the area of the circle, which would be pi r square, approximately 3.14 r square. These two are really not that different. This is slightly over 75% of this, but you only get roughly half the moment of inertia. So, and the reason to, you can explain that clearly is by looking at the difference between the two. The difference between them is this area that's out here on the perimeter, and that area is quite far away from the axis x. And so remembering that inertia is kind of like area distance square, you basically are summing all these effect of these areas and multiplying it by distance square, which amounts to a significant difference. Approximately twice as much inertia you get from the square as opposed to the inertia of the circle that is inscribed, even though their difference in area is not that much. So this is not a very efficient shape if you need to resist bending stresses, because it doesn't have much area that's far away from the axis that you are computing the moment of inertia around. So that's something very important to keep in mind.